So hello everyone, and welcome to the OneClass channel. My name is Donna Riel, and I'm a recent master's graduate in the Material Science program at the University of Ontario Institute of Technology, also known as UOIT and Ontario Tech. So today we'll be going over some commonly asked chemistry questions at both the high school and college levels. So if you need some help or tutoring, check out the links below in the description. Okay, so we're just gonna go over first question. Iron is one of the biologically necessary metals. Name 2 biochemical functions that it serves. I'm just gonna write it down. Iron. This is question 1. So one of the main functions of iron is that it is found in the protein hemoglobin. So hemoglobin is a protein that's found in your red blood cells. And what it does is that it binds to oxygen and also facilitates oxygen transport. From your lungs all the way through to your arteries. So one of the other iron functions is that it is also found in another protein called myoglobin. So myoglobin is found in muscle cells. And it's used for oxygen storage. Okay, so what myoglobin does, that it transports oxygen to the mitochondria of muscle cells. So now I'm just gonna look with these answers. Wow, so this is a long answer. Iron is needed in complex processes, that's true. Production of red blood cells, process known as hematosis, also part of hemoglobin. Yep. Metabolic energy. Yep, so this is a good and very descriptive answer. Answer is correct. I'm just gonna also say that iron is also used for the protein hemoglobin. Okay, so on to the next question. An amphoteric salt is one that contains an anion that can act as an acid or a base in water. Baking soda is an example. By combining the ionization and hydrolysis reactions of the anion, we get the principal reaction that occurs when this salt is dissolved in water. I'm just going to write down this reaction. It's 2 CO3 minus CO3, yes, sorry. Plus H2CO3. The pH for such a solution is pKa1 plus pKa2 over 2. Calculate the pH of sodium bicarbonate solution. So I'm just going to write that down. So what's missing is the pH of our sodium bicarbonate solution. Okay, so just looking at this question, so this is an example of a polyprotic acid. And the first thing we want to do is to find the Ka values of our reactants. So I'm just looking up on Google the different polyprotic acid Ka values. So Ka is the acid dissociation constant. So in our case, we're looking for carbonic acid, which is found here. Its Ka1 value is 4.2 times 10 to the negative 7, while its Ka2 value is 5.6 times 10 to the negative 11. So I'm just going to write these values down. So this is step 1. Question number 2. So first, the Ka1 value for this question is 4.2 times 10 to the negative 7. And the Ka2 value is 5.6 times 10 to the negative 11. Okay, so after we found out our Ka values, we go back to the question. Now we want to calculate pKa. For example, pKa can be calculated using the following equation, where pKa is equal to the negative log of our Ka value. So in our case, pKa1 is equal to negative log of 4.2 times 10 to the negative 7. And then this is equal to around 6.4. And we can do the same thing for our pKa2 value. Is equal to negative log Ka. So then we just input our value for Ka2, which is 5.6 times 10 to the negative 11. We get a value that's around 10.25. Then finally, the question asks, what is the pH of this sodium bicarbonate solution? So lastly, this is given in the question, where pH is equal to pKa1 plus pKa2. Undo that. pKa1 plus pKa2 divided by 2. Input our values, 6.4 plus 10.25 divided by 2. And we get a final pH of 8.35. Okay, so I'm just gonna look at answer. So they did the same thing. They found the Ka values, which was found in the table. They used the formula, find pKa. Okay, 6.4 and 10.25. calculated pH, and then substituted the values. I'm just going to say answer correct. And is correct. So on to our next one. So this one's kind of easy. When two pure substances are mixed to form a solution, what happens? So it's either A, heat is released, B, heat is absorbed, C, there is an increase in entropy, D, there is a decrease in entropy, or E, entropy is conserved. So this is question number 3. So basically we can rule out A and B. They don't specify what pure substances are being used, so we can't just assume that heat is either released or absorbed. So I'm just gonna rule out the first 2 options. And then the last 3 options talk about something called entropy. Let me just write this down. Okay, so if you don't remember what entropy is, basically when entropy is increased, there is an increase in randomness. Increase in randomness. So basically this can happen just due to a lot of different things. When there's an increase in temperature, there's an increase in entropy because the molecules tend to move faster and tend to get more disordered. In our case, we're talking about 2 pure substances that are mixed together. So I'm just going to write like a diagram of what these pure substances might look like. So let's say we have a pure substance A, which I'll draw out here. And you have pure substance B. So I just drew out the molecules and what they may look like when they're in their pure substance. You can see that everything is ordered when they're not together. But if I were to mix this up, mix the 2 substances together, you start to get an increase in randomness. So therefore, we can say that our answer is C, an increase in entropy. Let me just verify the solution down here. So again, when 2 pure substances are mixed to form a solution, there is an increase in entropy of the system. This is because there is an increase in the randomness of molecules or ions that they are distributed throughout the solution more rapidly. Okay, heat may be released or it may be absorbed as well, depending on the substances. Answer is C, there is an increase in entropy. This answer is correct. And just say solution is correct. Okay, so on to our 4th question. Estimate the pKa values of the functional classes represented by the given molecules. So this question just shows a lot of different molecules, and it wants us to kind of estimate what their pKa values are. Okay, so first I'm just going to write down what pKa is. So it measures how acidic your compound may be, and basically the lower the pKa value, the more acidic your compound is. And basically when you have a more acidic compound, this means that it's more likely to donate H+. Okay, so depending on the type of functional group that you have, these different functional groups correspond to different pKa values. So I'm gonna write out a table that shows from least acidic to more acidic, and also what their corresponding pKa values are. So I'm not saying you should memorize these values, but it's just good to know like the trend that you may see. So let's just say for the functional group that contains an sp3 hybridized carbon, typically has a pKa of around 50. Next, for sp2 hybridized carbons, its value is around 44. Amine groups, 38. So again, I'm not saying you should memorize these values, but it's just good to see the kind of trend that you get. And you start, like the more you do these questions, you start to memorize what their pKa values are. So I'm just gonna write them all down. sp hybridized carbons, around 25. Okay, I'm just gonna do the same table down here. For ketones, pKa is around 20. Alcohol groups are around 16. For water, it's around 15.7. So you can find these kind of tables online. Sometimes they're given to you in the question. For protonated amines, it's around 10. Carboxylic acid groups, it's around 5. So you can see that the functional groups tend to be more acidic now. Positive OH group, it's the most acidic, and it has a pKa of 2. Okay, so going back to our question, we have 6 compounds there. First one is an alcohol group. So since these values are in multiples of 5, we can say that this is around 15. Just looking at the table that I made. For this carboxylic acid group, it's here, so it's around 5. It's on the more acidic side. Next is this protonated amine group. It's here, so it'll be around 10. And next, this is an example of sp3 hybridized carbons. So its pKa around 50, so that shows that for this functional group, it's not likely to donate any of its protons. It's very happy where it is. It's a very stable molecule. The next is this terminal alkyne group. So alkyne is when there's a triple bond. This is an example of sp hybridization. So its pKa value is around 25. And lastly, we just have this amine group. And just write down N3. This is a secondary amine. So I'm just gonna say that it's around. So I'm just gonna verify the answer here. So they had 15, 5, 10, 50, 25, and 40. So therefore, this answer is correct. On to our next question. So I'm just gonna number. This previous question was number 4. So now we're on to question number 5. So of these molecules, these gases, which has the fastest moving molecules at a given temperature? I'm just going to write them down here. We have HBr, NO2, H6, or they all have the same average speed. So in order to calculate a question like this, we're going to use this equation. So this is a question that's made from Graham's law. And basically you can calculate the average speed of a given molecule by calculating their molar mass. So this is the long equation. It goes 8RT over pi m. So this is where m is molar mass. R is just a constant, 8.314 joules over mole times K. And T is temperature in Kelvin. So since these are constants and it just says at any given temperature, the only thing that really varies amongst all these different gases is their molar mass. So if you look at the equation, when you have a smaller molar mass, then that means it's a faster moving molecule. So what we need to do is we need to calculate the molar mass of all of these substances. First, I'm just going to Google molar mass of HBr. So the molar mass of HBr is around 80.91 grams per mole. The molar mass of NO2 is equal to 46. I'll just say 0.1 grams per mole. So the molar mass of ethane around 30.07 grams per mole. Okay, so next, now that we look at all of our different molar masses of these gases, we can see that the ethane is the lightest, so therefore it's the fastest moving molecule. NO2 is the second, and HBr is the slowest. So I'm just gonna write down C2H6 is the fastest. Moving molecule. Okay, so since this question only asks at a given temperature, then we can just kind of say the trends. However, if they gave us a temperature, like let's say if they gave us like 25 degrees Celsius, in order to calculate the speed, we would just plug it into the equation that I wrote down. But first you would have to convert degrees Celsius to Kelvin. So after you can do that, you can calculate how fast these molecules move at a given temperature. But in our case, I'm just going to say that ethane is the fastest and HBr is the slowest. Okay, so let's look at this answer. Graham's law implies that the lighter a gas's molecules are, the faster they diffuse, assuming all other things are equal. So therefore, the gas with the lowest molar mass will be the fastest one to diffuse. The molar masses of the three gases in your question are HBr and O2, yep, 80, 46, 30. Hence, the ethane moves fastest at a given temperature. I'm just gonna verify this. Is correct. I'm gonna say that. Okay. Okay, so those are all of the questions that we have for today. If you enjoyed today's question and answer session and would like to be notified of when to do this next, please hit the subscribe button and also the notification bell below. If you'd like to submit your own questions, then visit the links in the description. And also remember to leave a like and comment, and also share this video with all of your friends and classmates if you need any chemistry help. So this has been Donna from OneClass, and I hope to see you soon. Goodbye.